Hi, so welcome to Math 140 Calc 2, and we are in the final week of the semester. And what I want to do is I want to continue to talk about applications of math. What can you do with the stuff that we've done, as well as emphasize what other classes might you take after this. You should be considering either majoring in math and stat, or at least taking a few more classes to build up some skill sets that you can use in various things. And I want you to get a sense of, well, what would I do if I took a stats class? What would I do if I took another math class? What kind of problems can you study? And so what I want to talk about today is one of my favorite topics, the German tank problem. So I've given numerous talks on this over the years, and I've written a paper on this with some students at Williams, and I'm currently extending that paper even further with some additional students. So you really don't need much more than what you're doing right now to be at a position where you can start doing some new math. And this is math that has tremendous applications. All right, so what I want to do is talk a little bit about the history of the problem. So this is a link to a YouTube video on what is going on in Europe in late 1930s, early 1940s. Anybody want to tell me briefly what was happening? World War II, or at least the European part of World War II. There's a reason why it's called World War. It was happening in many other theaters as well. But you can see the massive gains the Germans made in the beginning of the war, just the number of countries that they overrun, or parts of countries that they overran. And a lot of it was due to a phenomenal use of tanks and very powerful tactics. And so for the Allies, the forces opposing the Axis powers, it was important to know how many tanks did the Germans have? How many were they producing? How many were in theater? So how do you figure out how many tanks the Germans have? What could you do? How could you find this out? Somebody give me a way. It may not be a good way. What could you do? Count them. How? Where? You see records? So go to the German tank factory and say, hello, Steve Miller, London Times. We're doing an article on German tank production, and we were wondering if we could interview some of your workers on the assembly line and just give us a sense of how many tanks you're producing. You could absolutely try to do that. You might be able to get the answers to your questions, but I don't think you'd be able to get back to London to write the story. So what could you do? Related to that, though, very similar to that. So you could try to look at how many tanks are in each battle. Especially if you win, you could look at the tanks afterwards. But going back to this idea of just showing up from the London Times, rather than being obvious and saying it from the London Times, what could you do instead? Well, you could try to do that. You could try to be a spy. You could try to pay somebody who works there to get you information. Or you could try to look at, what do we need to make tanks? What kind of raw materials do we need? Or are the motors for tanks being built in another place? And try to find out how many motors are being produced. So there's two main avenues. One is through spies, and one is through math. And so unfortunately, because of the Zoom window, it looks like the very bottom is cut off. Which do you think works better, spies or math, stats? Out of curiosity, what's the prefix of this class again? Probably math, given that I'm doing the lecture today. This is probably one of the success stories of math and stats. Not to put anything against the spies who risk their lives to get this information. But the goal of this is to show you how powerful math and stats can be. And just a little bit of my experience, my residential college, we had some incredibly interesting modern art, including a giant lipstick on a tank, which I looked at for several years. And so I have had lots of experience counting tanks. It's actually very easy in this picture. How many? One, yeah. All right, so after a battle, let's imagine you win and you can look at the tanks. And you see, the tanks are labeled S1, S2, all the way up to SK. So we CK tanks. And the question is, you want to try to figure out how many tanks were produced. We are going to make an assumption here, which was true at the time. that when you are creating the serial numbers for the tanks, you start at 1 and go 2, 3, 4, or you have something very similar to that. Can anybody give me an advantage of having consecutive serial numbers? Why might that be a good thing to have on the side of the people who are building them? If I give you, this tank has serial number, 1008, this tank has serial number, 4007. What do I immediately know about the two tanks? I'm sorry, when they were made. Why might that be useful? So if there's an issue with one, you might know which other tanks were maybe made at the same time in the factory, if you're having a recall order. What else? I'm sorry? Well, I mean, the Germans should know how many there are because they're making them. Oh, how new they are, exactly. When was it made? This is the newer one. The newer one hopefully doesn't need the same kind of servicing maybe as the older one. That maybe it's time for the oil change, maybe it's time for the new treads. And so you could actually have a longer digit where maybe you have different blocks that are consecutive in the blocks. And by just looking at the serial number, you can get a lot of information immediately about the tank. Maybe you could have some of it designating the factory where it was made. Some of it could designate, month and year where it was made. And so you can immediately look at a tank and say, this was made in the factory that had that issue. This is one of the tanks we have to look at carefully. So there's a lot of advantages on the production side of having things listed consecutively. The danger, and this wasn't realized at the time, was you are sending information out there. This is the 21st century. We are now very used to information being sent out there. And a lot of people are quite concerned about how much information is being sent out there. What do people know about you? There was an interesting story a few years ago where Target sent some coupons to a household, including items for expectant mothers. And the father was very upset to be getting, such a set of coupons. He and his wife were well past the age of having kids, and his kids were too young. Why are you sending me stuff like this? And the manager apologized. And then the manager followed up a few days ago just to send another apology. And the father had to sheepishly admit that the coupons were actually useful, that there were some activities going on with his children that he was not aware of. How did Target know before he did that he was going to become a grandfather? Correlated purchases. When you buy things, the computer links, people who bought this, what else are they likely to buy? You should see this now when you're watching streaming video. Here are the suggestions on other things you might like to watch, or maybe even news story. If you liked this news story, you might want to watch this news story. It's amazing how personalized these ads are. This is all data science, math stats, trying to figure out what is the most likely thing to appeal to you next. What I love about this is what Target did next. Again, in the interest of full disclosure, I think it's a little bit upset to be angry at a company for targeting you when their name is Target. You should expect something like that. But they didn't want to lose the ability to try to convince people to come to their store. Especially if you have little kids, one-stop shopping is wonderful. It's great if you can go to just one place, get everything done. So they want to still provide the coupons to drag you in. But people don't like often to feel like they're being targeted. So what they did is, in addition to putting in the coupons that deliberately fit what you were expecting to purchase, they put in coupons that were completely opposite of what you would expect. What would be the least likely items that this person would want, to make it look like it was a random set of coupons. Now, you might put certain coupons in a more visually strategic real estate location than others, but just absolutely wonderful in terms of just how they use the information. So again, you've got to be careful. What information are you giving away by what you do? And so over here, the tanks were labeled sequentially. Well, how much information does that give away? Imagine I'm trying to hire someone to do a project for my company, and they're very excited. We are so thrilled about the possibility of working with you. So my contract number would be 00000001. Who else have you worked with? And so a lot of times, things are just completely randomized. So you have no idea how much action has been happening. So you can disguise exactly what your participation is. I might have given this example in this class earlier. How many of you have ever gone into a restaurant or a bar where they have a tip jar? If you go to Lickety Split, you'll see a tip jar. At the start of the shift, what can you tell me about the tip jar? It's not empty. Or at least most places it's not empty. Why is there money? Somebody said, yes? Yeah, they put a little bit in so that people know, oh, tipping is done here. So they don't start off at 0, they start off at some higher number. And again, it doesn't really matter unless people are actually stealing money from the tip jar, which is really, really bad. You get that money back at the end of the night. And so one of the modifications I did with some students, which we recently published, was what if you don't start at 1? What if you start at some unknown number? Can you still try to figure things out? So we have a couple of unknowns here. So the first biggest unknown is how many tanks were produced. And then what we can do is, let's say we observe K tanks, and we're going to try to predict what is N based on the serial numbers that we observe. And all that we really need to look at is the largest serial number. So we will assume all the tanks from 1 to N are equally likely to be captured or to be found after the battle. An interesting problem might be, well, what if some numbers are more likely to be captured than others? What if there's maybe some correlations that it could be a very large battle and maybe whatever. So again, just writing things down mathematically, because that's one of the things we want to do, convert to math speed. From 1 to capital N, we observe K, the largest seen is little m, and we want to estimate N as a function of M and K. So we use the hats often to denote the estimate. So N hat is going to be a function of M and K. And then the newer version is we don't know what the lower value is. We just know that there's some value. We're not sure what it is. All right. There are tremendous dangers in overestimating or underestimating. Can anybody give me a danger in either direction from overestimating or underestimating?
Underestimating, you might not be prepared.
Okay, so let's say you underestimate. You think you're going to be facing 100 tanks and there's 1,000. What could happen?
You'd be like underprepared, you don't have enough resources there.
Yeah. Yeah, we just saw in the Battle of Trafalgar that if you are on the numerically inferior side, you could lose your entire force with very little damage to theirs. So you might think, okay, I'm facing 100 tanks. If I send in 250, that should be more than enough to blow them away. Oh my God, I'm facing 1,000. It's going to be a disaster. All right, so that's the danger of underestimating. What about overestimating? What is the danger of overestimating?
Maybe deploy too many forces.
Yeah, you deploy too many forces. You think, oh my God, we're going to face 1,000 tanks here. We've got to put everything here, or they're going to overrun Paris. And so you put everything there, and then you realize, wait, there's only 10 tanks in theater. They're attacking somewhere else. And so another battle in World War II, in the beginning, in the war in the Pacific, things were not going well for the Americans. And they intercepted a Japanese transmission saying that they were going to do an attack on AF-15, which we thought, have I told the story yet? Okay, they thought AF-15 was Midway. And at this point in time, the war was not going well in the Pacific for the Americans. I don't think they had any major victories. I think they had maybe one tie in the Coral Sea. But here was a chance to change the tide of war. If we actually know where the Japanese are attacking and we know roughly what their plan is, we can have our forces waiting. The problem is, what if AF-15 isn't Midway? What if AF-15 is, what if they're attacking Pearl Harbor again? Or going to Australia, or going to the West Coast, and you put your forces in one place and they're not there. So Admiral Nimitz told the code breakers, come back when you're sure. Pretty sure is not good enough. Before we go all in, we need to know. And the solution that Commander Rochefort came up is one of the most clever ideas I've heard in my entire life. It's very similar to the Steve Miller London Times. I was wondering if you could let me tour your factory. They basically did almost that. On a secure channel, they contacted Midway and they instructed them to break one of their water pumps and then have them broadcast a message either in the clear or in a code we knew the Japanese had cracked. level minor items, including the fact that we're going to be out of fresh water in 2 weeks if we don't get a new water pump. Needs transmission. And when they decode it, it says, we've just intercepted an American transmission from AF-15. They have a broken water pump and they will be out of fresh water in 2 weeks if it's not replaced. At which point now the Americans know AF-15 is Midway. And this was the turning point in the Pacific War. Fascinating battle in terms of what was done. One of the many points I will just mention is a lot of times in life, you do the best you can with the time that you have. And the Americans needed as many aircraft carriers as possible for the battle. The Lexington, I believe it was the Lexington, if not the Lexington, it was the Yorktown, was in Pearl Harbor for repairs and it needed to be there for about 2 months. And they said, we don't have 2 months, you have 2 days. Anything that can only be done in port, do that right now. And everything else, we're going to just leave the repair crews on you as you sail to battle. And you're going to just basically be fixing the boat right up until the battle and possibly during. And the ship was actually lost in the battle, but its planes played a key role in changing the outcome. So again, a lot of really good advices for when you leave Williams and you're trying to solve a problem. It doesn't have to be perfect. The phrase is, don't let the perfect be the enemy of the good, where you try so hard to get everything perfectly right that you don't do anything. Sometimes you just say, this is the amount of time I have. I'm going to do the best I can with the amount of time that I have. All right, so we've talked about the dangers of overestimating, underestimating. One of my favorite quotes is from President Lincoln. There's many different variants of this going back to the Civil War. If General McClellan isn't going to use his army, I'd like to borrow it for a time. So he had a reputation, well-deserved, of being a wonderful trainer of men and getting the army ready to fight. But he was always convinced that the Confederates had more troops than he did and that it was not the right time to engage in battle. And there were numerous opportunities where he had the numerical advantage over Lee, but just would not commit his forces. So I'll just leave it at that. All right, so what I want to do over the next day or two is talk a little bit about the mathematical preliminaries. What do we need to do this? So most of the time in life, you are not going to be able to get a beautiful closed form solution unless you're doing really good theoretical physics at the most fundamental level. When you do anything real world and you get your hands dirty, it's hard. You're going to often have to resort to numerical simulations. Did we do Monte Carlo integration in this class? I don't think so. Okay. So maybe we'll do that if time permits at the end. But most of the time you have to resort to computer simulations to evaluate problems. If you can get a closed form answer, that is much better. Because with a closed form answer, you can say, okay, well, let's see, what would happen if the price of oil raises another 30 cents? What would that do to the economy? What would be the impact of that on inflation, on GDP? Versus, well, we have so many complicated relations, we're going to just do a bunch of numerical simulations and have a window of where we think things will be. We saw this with the baseball paper, that we were able to get a closed form expression for the probability that a team has a given one-loss record, the Pythagorean one-loss formula. And then that allowed us to say, well, we have formulas that will generate for a team, or if they're a pitcher, will allow. And we can then see how valuable is it to sign them and get a sense of, is it worth spending money on this player? And if so, how much? So the ability to get a closed form answer is wonderful. For this problem, we actually can get a closed form answer for n as a function of m and k for our best estimate. And whenever that happens, you always want to ask, why the miracle? What was it that allowed us to do this? And for this problem, the miracle is going to come from binomial theorem. Binomial coefficients, Pascal's triangle. How many people have seen Pascal's triangle? Okay, this is the one. We start at 1. We might talk a little bit about the new version where you have an unknown start. It can still be done. The algebra becomes a bit more involved, the math becomes a bit more involved. And so, to be brutally honest, I'm not that excited about talking about it, but just saying it exists, it can be done, that's really what matters. I want to talk a little bit about regression and conjecture. So we did the method of least squares, correct? Find the best ways of looking at the error. We could look at just the difference, which is bad because positive and negative errors can cancel. We can look at the absolute value, but then it's not differentiable. And given that this is the second calculus class, and many of you might continue to the third calculus class, to lose all the techniques of calculus is bad. So we often use the sum of squares for the errors because then we can use calculus. And so I want to talk a little bit more about regression and conjecturing. So how do you come up with thoughts about what might be true? How do you look at data and say, the data suggests the following? It's not a proof, but this might be the relationship. All right, so mathematical preliminaries. So n factorial is the number of ways to order n objects when order matters. And we define 0 factorial to be 1. So we say that there's one way to do nothing. If I have 3 objects, how many ways are there to order 3? I have 3 choices for the first, times 2 then for the second, times 1 for the third. Then we have n choose k, n factorial over k factorial, n minus k factorial. It's the number of ways to choose k items from n when order matters. So I have n people and I'm choosing k people, say, to be student council members. And all council members are the same. Has everybody seen n choose k? Anybody ever read Dr. Seuss, the Starbelly Sneetches, the Sneetches? What kind of Sneetches are there? Star and no star. So n choose k turns out to be the same as n choose n minus k. And the way you can look at this is, if I'm choosing k Sneetches to have stars on their bellies, and only those k Sneetches have stars, then the remaining n minus k don't have stars. So a lot of times when you go further in mathematics, we have what's called proof by story. If you can come up with a way to describe what's going on, it's often much better than doing the algebra. You could, of course, go through and prove a lot of these results by just unwinding the factorials and just comparing things. But it's frequently easier and it gives you a better sense of what's going on if you can tell a story. One of the places that this often occurs is the binomial theorem. X plus y to the n is the sum of n choose k, x to the k, y to the n minus k. And the way you can see that this is true is, when I expand this out, I'm going to have n factors, x plus y, x plus y, x plus y, x plus y. From each factor, I choose either an x or a y. So the power of x can be anything from 0 to n. And if I choose k of the factors to be x, then the remaining ones have to be y. So if I want to have 5 factors of x, how many ways can I choose 5 of the factors to be an x? And choose 5. I could write this as n choose k. I choose k of the factors to be x, and then I have to choose the remaining n minus k to be y. Well, what's n minus k choose n minus k? 1. How many ways can you choose n minus k people from n minus k people? 1 way. Everybody's in. This is known as the participation award, which we give very frequently now in youth sports. Okay. So one of the most beautiful relations in Pascal's triangle is n plus 1 choose k is n choose k plus n choose k minus 1. So if I take any element like 6, 6 is equal to the number above to the left and plus the number above to the right. So 6 is 3 plus 4. 10 is 4 plus 6. Has everybody seen this relation before? So one way you could prove this is you could just do the algebra. And you could just multiply out n choose k, n choose k minus 1, n plus 1 choose k, and then cross multiply and do some simplifications. And at the end of the day, you will get the result. So you can prove it by brute force algebra, but I don't find it particularly enlightening. All right, so let's do a more interesting proof. Let's say we have n Red Sox fans, which is amazing given the season that they're having, but they have a loyal fan base. So we have n Red Sox fans and we have 1 Yankee fan. How many ways can we choose a group of k people? Well, we have n plus 1 people overall. So the number of ways we can choose k people is just n plus 1 choose k. So this is an example not only of a proof by story, but a proof by computing something 2 different ways. And the idea is, if you often have a difficult problem, if you can prove it's equivalent to something else which you can do, then you're done. All right, well, how can I form a group of k fans from n plus 1? I could be in the situation where I fortunately don't have the Yankee fan. So if I don't have the Yankee fan, there's 1 possible Yankee fan. I don't choose them. That's 1 choose 0. And now I have n Red Sox fans left, and I have to choose k people. It's times n choose k. Or I could choose the Yankee fan, that's 1, choose 1. And then I have N Red Sox fans. How many people do I have to choose at this point? K minus 1. And there's the proof. Now, what I like about writing it this way is you can see the tops always sum to N plus 1, and the bottoms always sum to K. That is not the case in the original formulation. In the original formulation, the left-hand side sum is N on plus 1 on the top and N on the right. And then we have K's and K minus 1s. What's 1 choose 0? How many ways can you choose no one from 1? 1. What's 1 choose 1? So both of these numbers are 1. So we're really just multiplying by 1. This is one of the most powerful techniques in the course, in all of mathematics. You can multiply by 1, and what else can you do? Add 0, right? But when we multiply by 1, it often gives us a better sense of what's going on. It helps us do the algebra. As you go further and further in science, a lot of the problem becomes trying to find a good way to look at your expression so that you can really see what's going on. And so when I write it like this, it makes it hopefully a little bit clearer. All right, so we have some other relationships. What's 1 plus 2 plus 3 plus 4 plus 5? So I'm going down the second diagonal, 1 plus 2 plus 3 plus 4 plus 5. Which is the number right below. What's 1 plus 4 plus 10? Yeah, so it looks like if I sum along a diagonal from top right to bottom left, the answer might be the number 1 level below to the right. If you look everywhere here, that is true. So the question is, will that continue to be true? So we'll prove that in a moment. What I will do here is I will just show some fun, completely unrelated pictures about Pascal's triangle. What I'm doing here is the original program I wrote has things oriented going from left to right. I've redone it so it's top to bottom, so it's a little bit more standard. So I've just rotated Pascal's triangle 90 degrees. It's just a little bit easier to print it that way. And what I'm doing is every place where there's an odd number, I put a dot. Everywhere there's an even number, I delete. Does anybody know what kind of picture this is? Fractal. Did we see fractals at the beginning of the year with Newton's method? We saw some Newton's fractals. Did we see? I think we might have seen these pictures there. Yeah. So again, just going back to what's going on. We're seeing Pascal's triangle. Here's the fractals hiding in, and I'm just rescaling it so that no matter how many rows I have, it's always compressed to be the same size. And you can see the fractal shape emerging. There's a link to the video if you want to see that. All right, so going back to what we were saying though about summing along the diagonals, the formula is the sum m goes from k to big N of m choose k is n plus 1 choose k plus 1. And this is what's responsible for the miracle for the German tank problem. This is why we can get a closed form solution. And one of the great challenges is just knowing what's out there. It's actually a little bit easier now, because if there's something that you need, what can you do? You don't know exactly what it is, but I need something along the following lines. What can you do? This is the 21st century. You need, look it up how. Google, some kind of web browser, do some search on the internet, right? In the old days, you had to have textbooks or journal articles, and you would have to go through and try to figure out, I remember reading in some math book a result about the following. Let me see if I can find it. Now, as long as you remember, wait, the professor was babbling about this a while ago. Oh, my notes are online. I can check. I can search. I can do keyword searches. Okay, now that I have the keyword, I can go to the internet, put in those keywords, and just try to find something. And so, the more identities you know, the better. So it's like, I wonder if there are any identities involving binomial coefficients. Let's do a search on identities involving binomial coefficients and see what comes up. There's a beautiful website called the Online Encyclopedia of Integer Sequences, where if you just type in a bunch of numbers, it will tell you all the sequences in the world that it knows that have either those numbers as the start or those numbers in consecutive order or relative ordering at some point. Incredibly powerful for giving you a sense of what to do. And then it will tell you all the stuff that's known about them. So here we have this beautiful formula that if we sum diagonally, it's equal to one level further down and to the right. And the way we're going to prove this is by induction. So I don't think we formally proved things by induction in this class. So this is one of the proof techniques that, I just want to give you a rough sense of what it is, because if you continue into pure math, you will see this more. Do not worry, nothing that we're doing this week is on the exams. This has been to just show you what's coming next in math and stats, and to just give you a little bit of a sense of how we do proofs. So the way induction works is you first show it's true at the starting point, maybe n equals 0, n equals 1, whatever. And then you assume it's true up to a certain level, and then show it's true for the next. So if I know that whenever it's true for n, it's true for n plus 1, well, if I know it's true for 0, 0 implies 1, I now know it's true for 1. If I know that it's true for 1 and 1 implies 2, I now know it's true for 2. And you just march up like a staircase. So we induct on n. So note first that k is fixed. Okay, so the first value of n, what's the lowest value of capital N that we can take? The sum goes from k to n. What's the smallest possible value of n? K, right? Your n, the upper value of the sum has to be at least as large as the lower. So if I take big N equals k, then I've just got one term, k, choose k, which is 1. And then on the right-hand side, I have k plus 1, choose k plus 1. So it's clearly true when n equals k. Okay, so now let's assume it's true all the way up to capital N and show that it's true for capital N plus 1. Well, if I have capital N plus 1, well, I can sum up to capital N, and then I just have that final extra term, which is n plus 1, choose n plus 1. By induction, I assume that it's true up to n, so I know that first sum is just n plus 1, choose k plus 1. I'm sorry, it's just, oh, there's a typo on this slide. It shouldn't be n plus 1 over here. This should be what? That should be k plus 1. No, I'm sorry, that should be k, because I'm just doing the last term. That n plus 1 should be a k. So I would then get n plus 1, choose k plus 1 from induction, plus n plus 1, choose k. Why does that equal n plus 2, choose k plus 1? It does say so down over here, but it's almost encrypted because you can only see some of the letters because of the zoom window. So why is that last equality true? Why does n plus 1 choose k plus 1 plus n plus 1 choose k equal n plus 2 choose k plus 1? We've seen that earlier today. That's just the Pascal identity. In Pascal's triangle, if I sum two elements that are next to each other, then the answer is one row down in between. So we just use Pascal's formula to finish the proof. All right, so that's all the preliminaries that we need. So we can now turn to the original version of the German tank problem. So what I want you to do is I want you to come up with some conjectures for me. So I don't care how bad the answer is so long as it's correct. Okay, if I ask you like we did last time, what's 1 plus 2 plus 3 plus 4, right? Give me a lower bound for that. We did that last time, right? A lower bound of 1, absolutely fine. It's not a great lower bound, but it's a lower bound, it's accurate. If you give me a lower bound of n, that's better. It's still not close to the truth, but it's accurate. If you give me e to the n, it's false. So can you give me any lower bounds or upper bounds on n as a function of k and m? So I want to try to estimate how many tanks there are, given that I observe k tanks and the largest serial number is m. Can you give me any estimates on n? It has to be at least this, it has to be at most this. Can you give me anything? It has to be at least k. The tanks go 1, 2, 3. We observe k of them. N has to be at least k. Okay. Can you give me another lower bound that might be better than k? It has to be at least m, right? The tanks are consecutive. M is the largest serial number observed. It's got to be at least m. So we know our best guess has to be at least m. If the tanks are numbered 1 to n, the largest tank you observe is 93, and you say, we think there's 50 tanks. You're an idiot. There's no polite way around this. They're numbered consecutively. You've seen a tank numbered 97. You can't guess 50. It could be 97 was the largest tank. It could also be the largest tank was 1 million, and boy, did you get unlucky. And this could then be an example of maybe some kind of bias in terms of how you're observing things. So we know n has to be at least m. If m increases, what do you think should happen to my estimate? Do you think it should go up or go down as m increases? Up. What about if I fix m and I increase k? Do you think my estimate should go up or go down? If I have, my largest tank observed is 100, and I observed only one tank, or my largest tank observed is 100, and I observed 50 tanks. So you think that as I increase k for fixed m, my estimate of n should go up. So again, imagine the extreme cases. I observe the largest tank is 100, and I observe just one tank. Or my largest tank I observe is 100, but I observe 50 tanks. Where do you think n is going to be larger? When I observe just one tank and the largest is 100, or I observe 50 tanks and the largest is 100? So what do you think? I'm sorry? It should go down. If I observe 50 tanks and the largest one is 100, then I'm thinking n is a little bit lower, because I have more of a chance of seeing something high. I could have been a little bit unlucky. If you only observe one tank and you observe 100, if you had to guess, what might you guess the largest tank is? If you're observing 1 through n, what might you guess your smallest tank number would be? I'm sorry, you're observing tanks 1 through n. If you had to guess what number you observe, what would you guess? If you observe 1 to n, you would guess what? I'm sorry, n over 2. If I have n numbers and I choose one at random, odds are I chose something near the middle. So if I had to guess how many tanks there, maybe I would say if I observe 100 with one tank, maybe there should be 200 tanks total. But if I now observe 100 as my largest one, and I have 50 observations, it seems unlikely that it is as high as 100, as high as 200. I've had so many opportunities to get something near 200, and I'm not. The more observations I have, so I need a function that increases with m and decreases with k. Can anybody give me a function that increases with m and decreases with k? Function of m and k that increases with m and decreases with k. So you need to conjecture now. So what would be a function that increases with m and decreases with k? Give me a function that increases with m. Simplest function you can think of. I'm sorry? 2m or n? 2m. Okay, but let's just say some constant times m. Okay, constant times m increases with m. Give me a function that decreases with k, a positive function that decreases with k. Constant over k. So give me a function that increases with m and decreases with k. M over k, constant m over k. So let's try, our expected value is m plus maybe some constant b times m over k. As I increase m, it's going to go up. As I increase k, it's going to go down. It turns out the answer is m times 1 plus 1 over k minus 1. So it's almost perfectly m over k. Now, whenever I ask, is this reasonable, you always want to look at extreme cases. There are some values of k and n that would be wonderful extreme. So give me an interesting value of k. Okay, we have to observe something. So if we take k equals 1, we already talked about how we think we would be around n over 2, so that the number of tanks should be roughly twice m. And if you take k equals 1, you see, yeah, it does look like n hat is twice m. All right, that looks reasonable. What's the other extreme? So one extreme is k equals 1. What's the other extreme? K equals what? So if K equals M, then you observe K tanks, and the largest one is K. That's not quite the right extreme. You're close. K equals N. You happen to observe every single tank. If K equals N, well, let's see what would happen. What would M equal if K equals N? There are N tanks, you observe all of them. What's the largest serial number you observe? N. So in that case, M would equal N. You get N times 1 plus 1 over N minus 1. That's N plus 1 over, that's N plus 1 minus 1 is N. This formula works on the extreme cases. So this is a great way to see if this formula is reasonable. It passes the sanity checks. When K equals 1 and K equals N, it gives us a reasonable answer. So this is not a proof that the formula is right, but it's a good start. So the next thing is we need to calculate what is the probability that the largest serial number is little m, given that we observe K tanks, and the largest tank, the number of tanks goes from 1 to capital N. And so I claim the probability is just this difference of binomials divided by n choose k, which can be simplified. And there's a couple of ways to prove this. So one way is, this is very similar if you ever did these problems in high school. I'm choosing a hand of 5 cards for poker. There's 52 choose 5 ways to choose 5 cards from a deck. If I have capital N tanks and I want to choose K tanks, that's just n choose K. So that would be the denominator. I have n choose K ways to choose K tanks. I want the largest serial number to be m. How can I do that? Well, if I want the largest serial number to be at most m, then all K tanks have to be chosen from 1 to m. There's m choose K ways of doing that. But that doesn't mean that I chose tank m. It just means I didn't choose anything larger than m. Now, if I look at m minus 1 choose K, that's how many ways I can choose the tank whose largest number is at most m minus 1. So if I look at the difference is going to then just be the number of ways where m is the largest tank. And then by using Pascal, that's the same as m minus 1 choose K minus 1. Another way of looking at this is I could say, I choose that tank m. There's one way to do that, 1 choose 1. And now I have to choose K minus 1 tanks from 1 to m minus 1, which is m minus 1 choose K minus 1. So you could actually prove Pascal's identity by just counting tanks. So we now have this formula. And then this just goes through what I just said. So now in probability, you'll talk about the expected value. So if you've ever been in a class where everything is not weighted equally, you've seen expected value, 45% final, 40% midterm. You take each thing, multiply it by its weight, and then sum them. So the expected value of some random variable m is just the sum of m times the probability that you get m. And so when we substitute, we get the sum of m times m minus 1 over K minus 1 choose n divided by n choose K. And now we get to do all of this wonderful combinatorial algebra. We don't have that much time. Anybody have any quick thoughts about how we might try to evaluate this sum? What could we do to things on the right-hand side? What do you know about n choose K? What is n choose K? So we have to just use the algebra of what these expressions are. So we just substitute. We expand out what does m minus 1 choose K minus 1, what does n choose K. We put everything together and we see a lot of things start to cancel. And when you keep doing a bunch of the algebra, you can pull everything outside the sum that doesn't depend on little m. And then we're left with the sum of m choose K. Oh, wait a minute. We're summing m choose K, m goes from K to n. This is the identity I mentioned earlier in the day. This is why everything is nice. This is just n plus 1 choose K plus 1. So you can look at the algebra. There's absolutely nothing deep about this algebra. It's just roll up your sleeves and just keep working until you get something nice, noticing that a lot of things cancel. And then we just put in, it was n plus 1 choose K plus 1. We put in what n plus 1 choose K plus 1 is here, and then a bunch of terms cancel, and it becomes K times n plus 1 over K plus 1. So just rewriting that on the next slide, we show that the expected value of m, the expected largest serial number we observe, is k times n plus 1 over n plus 1. Well, we can use this to solve for n in terms of the expected value in k. So we just multiply both sides by k plus 1, divide by k, subtract 1, and we get n is equal to the expected value of m times 1 plus 1 over k minus 1. And so now to get our formula, we just say, okay, well, we don't know the expected value of m. We'll put in the value we observed for m. And we'll use that to get our best guess. And then in statistics, I'll talk about all the different kinds of biases and whatnot and estimates like this. But this is a great way to get a test statistic to get an estimator from our data. And we now estimate the number of tanks as m times 1 plus 1 over k minus 1. And except for the minus 1, we actually saw that something like this was pretty reasonable. If we just posit goes up with m, goes down with k, has to be at least m. So this was not an unreasonable answer. The new version, is just what happens if you now have to observe tanks starting from big N1, but we don't know what that is. So we talk now about the spread, the largest minus the smallest. If I want to estimate the mean, the average value, how many data points do I need to estimate an average value? If I want to calculate an average, nope. 1. If I have 1 point, I can estimate the mean. Somebody used me to estimate an entire population once. And I had to apologize to everybody in that population because I am not a good representative. I'm not even in the population, but 1 person is enough to give you an estimate for mean. If you want to talk about fluctuations about the average, how many observations do you need for fluctuations about the average? If you want to estimate how many people have seen standard deviation or variance. So how many data points do you need if you want to talk about a variance or standard deviation? You need at least 2 points. So if I want to try to estimate, well, if I don't know N1 and I don't know N2, I need K to be at least 2. I can't say anything reasonable with one estimate, with one observation. And so you get a very similar formula, but instead of dividing by K, you divide by K minus 1. Basically, because you never want to try to do this when you only have one observation. And so the formula becomes S times 1 plus 2 over K minus 1 minus 1. So this actually is not an unreasonable formula. The K minus 1 makes sense because I should never be doing this with just one measurement. And the factor of 2, well, before I had one direction that I can move, now I have 2 directions that I can move. So, okay, I can see maybe the 2 coming in like that. So you have a slightly more involved formula. If you want to calculate what's the probability that the spread is S, it's a little bit worse than last time, but it exists. And then the rest of the proof is very similar to before, but the algebra is a bit more involved. All right, so the final slide for the day, and this is going to be beautifully timed to 50 minutes. After the war, we were able to get the actual production numbers. So we have the statistical estimates, we have the intelligence estimates, nice round numbers for the most part. Who thinks that the stats math people did better? My hand is up if that helps you at all. Okay. Do you think it was by a lot or a little? Do you think they were close or just better? Those numbers are phenomenal. Much closer to the statistical estimates, 327 versus 342, 244 versus 271, 169 versus 120. Absolutely amazing. All right, so this ends part 1 of the lecture. So the next part on Wednesday, we will be talking about applications with regression and trying to find out these formulas numerically. All right.